Okay, so what we're going to do is use what's called the second derivative test. Okay? So second derivative test. So this version kind of involves all sorts of our second partial derivatives, right? Because now we're working in multivariables. So you're going to be using partial derivatives, right? So what the first thing, the groundwork, I guess you could call it, is what's called the discriminant. Okay, so the discriminant is denoted as a big D, capital D, and then evaluated at the point AB. That's going to be equal to f sub xx evaluated at AB, f sub yy evaluated at AB, minus f sub xy evaluated at AB, and this one is squared. This last term is squared, okay? Alright, so what does this mean? Well, it's kind of just a convenient way to analyze like what's going on at this point. Are the slopes going up in all directions, or is it going down in all directions from that point, or is part of it going up, part of it going down? Anyways, we'll go into details about what this tells us. But for right now, it's good to know that this is the second derivative, or the second partial, taking the partial derivative with respect to x and then with respect to x again. This one is the result of taking the partial derivative with respect to y twice in a row. And this one is obtained by taking the partial derivative with respect to x and then to y, or even the other way around. Remember, you can do it in any order. That's what Clairaut's theorem says. Okay, so anyways, so from here, we're going to use this equation. This one's pretty important. This is essential to the second derivative test. That's pretty much the backbone of it. And then, so we're going to say that if, so this is the latter part of the second derivative test. We're going to say if P, which is AB, let's say that is a critical point, okay? Is a critical point. So critical point meaning that our both of our first derivatives, our first partial derivatives, are either equal to 0 or do not exist, one or the other, or both at the same time, right? So critical point of f of xy, our function, then. And we have to assume things. Assume that f sub xx, f sub yy, and f sub xy are continuous near P. Because if they're discontinuous, that kind of just throws a wrench into things. But you won't have to deal with this in problems and stuff. They'll pretty much all be continuous. Anyways, okay. So this is just conditions that we have to lay out. So near P, then we say that. So basically, there are 4 different things that can happen. So the first thing is if our D, if this whole entire thing on the right side, if that all turns out to be positive, so greater than 0, and if f sub xx at AB is greater than 0, then we have that f of AB is a local minimum, okay? Local minimum. All right, and then we have, so these are kind of, you just have to kind of memorize these, sort of. I will go into detail about why these are true, okay, why these statements work out the way they do. So if your discriminant turns out to be positive again, but this time our f sub xx at that point, AB, turns out to be a negative value, then we have that f of AB is conversely, a local maximum. Okay? And I have 2 more possibilities for the second derivative test, which I'll continue on the next slide. So then we have number 3. If we get that our discriminant does turn out to be negative, then we say that f, our function, f of xy, has what's called a saddle point. Okay? At AB. Okay, and this is basically just what it sounds like. It looks like a saddle, literally. But, okay, and like I said, I'll go into more detail as well, just explaining and graphically as well. Okay, so the 4th option and the 4th and final one is if D is equal to 0, if it turns out like that, then that tells us that the test is inconclusive. Okay, so when the test turns out to be inconclusive, then we have to turn back to the first derivative test and see what's going on around that point. Okay, so anyways, let's go and I'll explain why these four options are the way they are, or why the four statements are true. So first of all, let's write down what is the discriminant again. So the discriminant at AB is equal to f sub xx at AB, evaluated at AB, f sub yy evaluated at AB, minus f sub xy evaluated at AB, and this term is squared, this last one. Okay, so let's look at the equation first of all for the discriminant. So this thing over here, this last term, anything squared is always going to be a positive number, right? Either 0 or positive, right? So it's never going to be negative. So we're always going to have subtracting some number, some positive number, okay? So everything basically depends on what's going on in the beginning here, in this first term. These two things multiplied times each other. So let's look at our first option. So our first option was if D is greater than 0. So if the determinant, if this whole entire thing turns out to be positive, that would imply that our both of these have to be the same sign, right? Our fxx and fyy must be the same sign. Must be same sign. Okay? Otherwise, we would get a negative number, right? Otherwise, we get a negative number in front if they're opposite signs, and then minus another positive number, so that would be overall negative, and that's not possible if we want our D to be positive. So that requires our fxx and fyy to be the same sign, okay? So, and then also there's the condition that if fxx is greater than 0, so if fxx is greater than 0, that implies that fyy is greater than 0, which, what does this mean? So now that both of these are positive, we decide both of them are positive. So what this means is that on a graph, in both directions, in the x and the y direction, on our 3D graph here, both in the x direction and the y direction, our graph must be concave up. Remember that? So we're going to have concave up in both directions, okay? So what we have is kind of like a bowl shape going on, okay? So it's going to be like that, so that means that we must have, the point here must be a local minimum. Local minimum. And this, again, this is when our D is positive, our discriminant is positive, and our fxx and fyy are both positive, okay? And the other one that's kind of an offshoot of this one, the other option, the way it could go is we have our discriminant being greater than 0 still. So fxx and fyy must be the same sign, but this time let's say our fxx is less than 0, okay? So that implies, since they must be the same sign, fyy must also be less than 0, so that's a negative value. So that means that it's concave down in both directions. Concave down in the x direction and concave down in the y direction. So if we have our point here, we have concave down in the x direction and concave down in the y direction, that implies that this point that we're looking at is a local maximum. Okay? Alright, so that's the first two. Now let's move on to the last couple options. Well, yeah. Okay, so number 3 option is if D is less than 0. So that implies that our I'll write that formula again. So D is equal to fxx, fyy minus fxy squared, right? So we already said this is always minus a positive number, so it'll be a negative number back here. So it depends on what's going on in the front. So if D is negative, that implies that we have a negative number or a 0 here, okay? So this must be negative, so that means that fxx and fyy have opposite signs. Opposite signs, okay? Alright, so that means that fxx could be positive, and then that means our fyy is negative, or it could be flipped, right? fxx is negative, fyy is positive. So either way, let's say that just means that, let's say this is the point we're looking at, point P, okay? So this means that this is our first option, or this is our, and this is our second option. Basically, it just means that in one direction, let's say in our x direction, it's concave up, right? And in the other direction, in the y direction, it's concave down. So it looks something like that, right? And when you draw the graph, it's a little bit tricky, but anyways, when you draw the graph, it's kind of going to look like a saddle, okay? So in the y direction, we keep going down, 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 but in this direction, we keep going up, up, and up, concave up, okay? So Sorry if the depiction there doesn't look too pretty. I'll admit that it does not. But anyways, so it looks like a saddle. That's the basic point. That our fxx and fyy don't agree. They're going in opposite directions. Okay? Alright, so that's basically it. I'll just write like a handy little chart for the second derivative test, just so you guys can see it in a more like concise form.
You go sexual city.